So we're going to talk about apportionment, specifically to the House of Representatives. So let's just define that first. And so these are definitions. I would definitely write down these definitions. Again, you can put them in your own words to shorten them. But for the House of Representatives, apportionment is just the process used to divide the available seats among the states. So that's specific to Congress, but more generally, apportionment is just the process used to divide any set of people or objects among individuals. And so we say we only use it for the Congress because for the House, your number of representatives depends on the size of your state's populations, whereas for the Senate, every state gets 2 senators. Everybody gets the same amount. All right, so get your definition of apportionment down and let me know when you're done with a green check so I can move on. And the House of Representatives requires a few more little definitions. Don't write down all of this nonsense. Here's what I want you to write down. I'll circle it in purple. We have this thing called the standard divisor. To get the standard divisor, you take the total US population and you divide it by the number of seats in the House of Representatives. That's called the standard divisor. And then the other thing you need to write down is this. The standard quota. Each state has a different standard quota. You take the state population and you divide it by the standard divisor. And so the standard quota basically represents how many seats each state should be allowed, but it doesn't come out to a whole number. So it's how many seats each state gets if fractional seats were allowed. Now, fractional seats are not allowed. You can't have like 14 and a quarter seats in Congress for your state, right? So we have to figure out a fair way, essentially, to deal with that decimal. How do we round this to a whole number? Which actually turns out to be a little bit more of a complex problem than one might think, right? You might be like, I don't know, just round it down or whatever. But you can give certain states more voting power than other states, which can become a real issue in equity if you just do that. So there were a bunch of methods devised that we are now going to talk about. All right. Okay, the 2010 census lists a population of 989,000 for Montana and 564,000 for Wyoming. Using these census data, find the standard quota for each state. The 2010 apportionment left each of these states with a constitutional minimum of 1. Compare their standard quotas to their actual representations. Before we can do this, we need to know about the standard divisor. So I need to give you some census info about the US from that year. First of all, there were and still are 435 seats in the House of Representatives, okay? The US population as of 2010 was 309 million. So the first thing we need to do is find the standard divisor. right? Which based off the last slide, whoops, the standard divisor is just the US population divided by the number of seats. So that's going to be my 309 million. Whoops. Divided by my 435 seats, which if we pop that into our calculator, gives us approximately 710,000. All right, so now we can find the standard quota for each of these two states. So my standard quota, let's say Montana. What's the abbreviation for Montana? Is that MT? I think so. So my standard quota for Montana, if I go back, the standard quota, we take the state population and we divide out the standard divisor. So I'm going to take my state population of 989,000. I'm going to divide out my state population of, nope. I'm going to divide out my, standard divisor of 710,000, right? It goes state pop divided by standard divisor. Great, we pop that into my calculator and I get about 1.4 as my standard quota for Montana. So if fractional seats were allowed, Montana would get 1.4 congressional seats in the House of Representatives. All right, so now let's look at the standard quota for Wyoming. So we're going to take Wyoming state population, which is 564,000, divided by our standard divisor. We're going to pop that into my calculator, and we're going to get about 0.79. So if fractional seats were allowed, Wyoming would get less than a seat in Congress, in the House of Representatives, I should say. But there is a constitutional minimum of 1 seat per state. So each of these actually, in reality, since you cannot have fractional seats, got the constitutional minimum of 1 seat. So there we go. That's reapportioning 14 of its elementary teachers among its 3 elementary schools, which have enrollments shown in the table on the next slide. Find the standard quota of teachers for each school. So in this one, don't write everything down, just write reapportioning 14 teachers. And so this is just an example that wouldn't be specific to Congress, but remember, apportionment just means dividing objects or people among certain groups. All right, and so here's our enrollment. So these are like our student populations for 4 schools in the district. And so the first thing you would want to do is find the standard divisor, which would be, let's first add up and find the total number of students, the total population of students, which they already did for us, right? If we add the students at Washington to Lincoln to Roosevelt, that gives us a total of 448. And to find the standard divisor, you would take the total number of students and divide in the total number of teachers, which gives us a standard divisor of 32, right? So this is, again, an analog of, we took the total US population and we divided the number of seats we had to distribute in Congress or in the House. But in this case, we're just doing total of students divided by total number of teachers. That gives us our standard divisor. Then to get each standard quota, we just take the number of students at that particular school and divide by the standard divisor. So for Washington, I would get 197 divided by 32, which is 6.156. For Lincoln, 106 divided by 32, so 3.3125. And for Roosevelt, 145 by 32, which is 4.53. And so this just gives us a fair way to distribute those new 14 teachers among the 3 schools in the district by student population. Now, the issue is we can't put 0.15625 teachers at Washington, right? It doesn't make sense. You either have to give them 6 or 7 teachers. Same thing for Lincoln. You either have to give them 3 or 4. And Roosevelt, you either have to give them 4 or 5. So what we're going to get into now is, okay, how do we fairly figure out how to round these numbers appropriately to distribute the seats in Congress, or just more generally to apportion anything fairly? All right, give me a green check when you're done with that example, and I will move forward. Okay, so our first method of dealing with those decimals in apportionment is called Hamilton's method. So definitely write down the title is Hamilton's method. So first thing you do with Hamilton's method is round down. So again, you don't have to write all this down verbatim. I would do it bullet points. You start by just rounding everything down, which means you're just chopping off the decimal. You're truncating it, okay? This is called the minimum quota. Once you've chopped everybody's decimal off, you're going to add up the minimum quota. So you're going to add up the totals. If that adds up to 435, you're done, because you've already given away all the seats, right? Now, if there are seats remaining, that's what the second point is going to tell us to do. You're going to look at each state's fractional remainder. And then you're just going to give an extra seat to the state with the highest fractional remainders until all the seats are gone. So this is a pretty simple method. Find all states' minimum quotas, give them their minimum number of seats. So just chop off the fraction. Now, if there are 3 seats left over, like we only added up to 432, good, you have 3 more seats to distribute. You're going to give the first seat to the highest fractional remainder, the second seat to the state with the next highest fractional remainder, the third seat to the state with the third highest fractional remainder, and then you're done. Does that make sense? Give me a green check when you're done copying this down. Yeah, Roosevelt, right? So if we took off the minimum quota from Roosevelt, we'd just be looking at 0.53125, which is larger than either of the other fractional remainders. So Roosevelt gets the extra teacher. So the final apportionment would be 6, 3, 5, distributing our total of 14 teachers. And that checks out. There are some issues with Hamilton's method. The first one is called the Alabama paradox. And that occurs when we increase the number of seats, yet some states lose seats as a result. It's a weird thing that could happen. I'll show you an example. The second one is the population paradox. And that's when a slow growing state gains a seat at the expense of a faster growing state. And the last one is the new states paradox, which can occur when the apportionment for existing states changes as a result of additional seats being added to accommodate a new state. So I would get all three of these down. Let me clear out the green checks. These are actually important. They're vocab terms you need to know. And then just give me a green check when you're ready to move forward. Docs. I'm going to give you a situation in which we have, let's say we had this specific population. So we have 4 states. I'm going to have you kind of copy down part of this table. We're going to call them states A, B, C, and D. And then your first row, just write down the population of each state. So the population of state A is 936. The population of state B is 2726. C is 2603. And D is 3735. That gives me a total population of 10,000 in our little country that has 4 states in it, right? All right, so the second row, here's what they've computed for us. Let's say we had 100 seats in our house to distribute. So we want to apportion 100 seats. The first thing we do to find the standard quota is divide our state population by the number of seats, right? By the 100. No, I'm sorry. The first thing we do is get our standard divisor, which is our country's population, which is 10,000, divided by the number of seats that we have. So divided by 100. So our standard divisor is still 100 because 10,000 divided by 100 is 100. All right, and then to get the standard quota, we're going to take our state populations and divide by the standard divisor. So each one of these state populations, if I divide that by 100, that's going to give me my standard quota, right? Divided by 100 and so on. And so again, the standard quota is like how many seats each state could have if we allowed fractional seats, right? But we can't allow fractional seats because there's no such thing as 0.36 of a person. So we're going to use Hamilton's method, which is first figure out the minimum quota. That's my next row. Chop off the decimal and just write the whole number that remains. So the minimum quota for state A is 9, B is 27, C is 26, and D is 37. Questions so far? We then add up our seats from our minimum quota and see if there's even a problem. If those add up to how many seats we have to give, that's great, we're done. But if you add those up across, we've only apportioned 99 seats. We have 100 seats to apportion, so we still have to give away 1 seat, right? So Hamilton's method says, okay, which state has the largest decimal? They get the first leftover seat. In our case, state A has the largest decimal, which is 0.36. So state A gets that additional seat. So instead of 9, they get 10. And this is what our final apportionment will look like. 10 for A, 27 for B, 26 for C, and 37 for D. That adds up to a total of 100. So here's where the Alabama paradox comes in. Well, what if we look at the total population, and the total population has increased to a point that we would like to add another seat to Congress? So now, instead of 100 seats, let's look at what would go on if we had 101 seats to distribute. Well, now we need to calculate a new standard divisor, right? So our new standard divisor is still our population, but now it's divided by 101 instead of 100. So now my standard divisor comes a little bit smaller. It's 99. If you pop this in your calculator, 0.0099. And so now, instead of dividing each state population by 100, I'm dividing it by 99.0099, which is a slightly different number. You might think, what kind of impact could that possibly have? Well, it's not really going to have any impact on the whole number part of this, but it will impact the decimal part of this. And the decimal is the thing that decides who gets the additional seats, right? And so if I divide all of those state populations by 99.0099, here's what my table looks like. So each one of these I've divided by 99.0099. So there's my standard quotient for A, 9.45. For B, 27.53. For C, 26.29. And for D, 37.235. So if I go back through the whole process, finding the minimum quota, chop off all the decimals, and look at what we got. So we got 9, 27, 26, and 39. Or sorry, 37. We total those up, we still have 99. But now, since we have 101 seats to give away, we have 2 left over instead of 1, right? Okay, so how are we going to figure out those 2 left over? Let's look at the remainder. Let's look at the decimal that we chopped off. Well, now the decimals all changed pretty drastically. D has the largest decimal. So we're going to give one of those 2 seats to state D. B has the second largest decimal, so we're going to give one of those 2 seats to state B. And so state B goes from 27 to 28. State D goes from 37 to 38. And then A only gets 9 and C only gets 9 or 26. The paradox there being everything stayed the same except we added another seat to Congress, right? And yet state A kind of got the short end of that stick because even though we added a seat to Congress, they lost a seat for their state. So that's an example of the Alabama paradox. So for Jefferson's method, we start with our state population. The first thing you would always do is you want to get your standard divisor, right? And your standard divisor is your country's total population divided by the number of seats that you have to give away. And so that gives me a standard divisor of 100. That's what I divide into every state's population to get its standard quota. So divided by 100, that gets me 9.36. Divided by 100, that gets me 27.26, and so on, right? To get my minimum quota, I then chop off the decimal. Done and done. So my minimum quotas are 9, 27, 26, and 37 respectively. Add those up. We've given away 99 seats. That's not enough. We still have 1 seat remaining. So here is what Jefferson's method says to do differently. Now we're going to divide by a smaller standard divisor. We're going to modify our standard divisor, which was 100. And we're going to choose a smaller one. So let's go to 99. So instead of dividing these by 100, let's move it to 99. Let's divide this by 99. And that'll give us new numbers. All right. And so when I do that, that gives me a new, what I'll call a modified quota, because it's not a standard quota anymore. I used a different divisor, right? But it gives me new decimals and new numbers. And then I'll chop the decimal off of that. So I chop the decimal off of those numbers, and now I get 9, 27, 26, and 37 again. So it didn't change my decimals enough to really make any impact. I'm still left over with 1 seat to give away. So I go back again, and I'm going to modify my divisor even more. I'm going to change it to an even smaller number. Now I'm going to divide everything by 98. And that's going to give me a new modified quota. Chop all of the decimals off that. We have 9, 27, 26, and 38. Well, notice that that did produce a different result because now state D got 38 instead of 37, and now they do total up to 100. Does that make sense? And so you just keep decreasing your divisor until you end up with decimals where when you chop off numbers, where you chop off the decimal place, it adds up to the total number of seats you had to give away. So that is Jefferson's method. In the chat, any questions on that one? Whoops, I got a question in the chat. Yeah, Naomi, great question. So you really won't be asked to do this. They will tell you, use Jefferson's method with this modified divisor. They'll tell you what it should be. You won't have to just think about how much to take away from it. Great question. All right, let's keep going. We got a couple other methods. The quota criterion says, and this is an important one to write down, for fair apportionment, the number of seats assigned to each state should be its standard quota, either rounded up or down. So whatever its standard quota is, it should be either the next number up or the same number just with the decimal chopped off. If it's not that, then we say that the apportionment method did not satisfy the quota criterion. Go ahead and give me a green. All right, consider a 4-state legislature with 100 seats. So use Jefferson's method to apportion the 100 seats. Is the quota criterion satisfied? So again, I'm just going to ask you to follow along here. You don't have to write this down. I'm just going to analyze the table, and if you have questions, ask them while you have them. So here's how I would organize this. First, we'd come up with our standard divisor. So you take your total population, which was 10,000, divided by the number of seats, in this case, 10. And we get a standard divisor of 100. So we're going to take each state's population, so state A, B, C, and D, and divide by that standard divisor of 100. Right? And that's going to give me my standard quota for each state, which is how many seats each state should have if we allowed fractional seats. To get the minimum quota, we just chop off their decimals. And then we total up what we have. Okay, well, we've only given away 97 seats, which means we have 3 remaining, right? So Jefferson's method says, okay, well, what we need to do is modify this divisor. We need to make it something smaller. And then we'll divide by that modified divisor, and then we'll redo it. We'll chop off the decimals and see if we've given away enough seats. So here they did it. They jumped straight to 98. So again, to Naomi's question, you're never going to have to make up the modified divisor. They'll give it to you. So if we use a modified divisor 98 and we divide all of these by 98 instead of 100, the totals we end up with are down in the bottom. We end up with these new decimals, right? And then if we chop off the decimal, we just truncate and total up what we have. Boom. We've given away all 100 seats there. Now the quota criterion says if we look at the original standard quotas, then the number of seats each state should get should be the whole numbers that surround that decimal, meaning A should only get 6 or 7. B should get 16 or 17 seats. C should get either 10 or 11, and D should get 65 or 66 by the quota criterion. Does that make sense? It should either be the next lowest number or the next number rounded up. And so what we want to do is compare this, the total outcomes, to the quota criterion. Was the quota criterion satisfied here? Well, A got 6, yep. B got 16, yep. C got 11, yep. And then D got 67. D should have only gotten 65 or 66, so it fails the quota criterion. Make sense? All right, I think we have a couple more, one or two more methods. Webster's method is similar to Jefferson's method. Okay, meaning you find the minimum quota, just like you do in all the methods. You start with your standard quota, you chop off the decimal, there's your minimum quota, right? Except that Webster's method seeks modified quotas that give correct total number of seats by using standard rounding rules. Meaning, if the minimum quota doesn't do the job, so you chop off all the decimals and you add up the seats you've given away, if that doesn't add up to a total of how many seats you have, then you go back to the standard quota and you just round it like you normally would. You guys are familiar with regular rounding rules. You round up if the decimal is 0.5 or above. You round down if it's 0.4 or below, right? We take our 4 states with our population of 1,000 and our 100 seats to give away. We find our standard quotas here, chop the decimal, we get our minimum quotas, we total it up to 98. You do the same thing that you would have done with Jefferson's method, which is you come up with a new modified divisor. They used 99.85, so they divided, instead of by 100, they divided everything by 99.85. Again, you will not be asked to figure out what modified divisor you should use. You'll just be given it. So then you divide everything by that, you get a new decimal. But the thing you do with Webster's method is you just use standard rounding rules. So you take those decimals and you round them as you would in standard rounding rules. So 9.4 rounds down to 9, 7.5 rounds up to 8, 6.4 rounds down to 6, 76.6 rounds up to 77, 100 oh no, sorry, that's it. After you've done that, total them up, and we got 100. Okay? So Webster's method, you're using standard rounding rules after you've found your modified quota. We got one more, folks. The Hill-Huntington method. This is it. It's identical to Webster's method, except it uses what's called a geometric mean. Write this down. A geometric mean of any two numbers is where you take those two numbers, you multiply them, and then you take their square root. Four states with the same populations and the same number of seats to give. So our standard divisor comes out to 100. And our standard quotas, we just divide our populations by 100, are given here. Chopping off the decimal, there's our minimum quotas, and when we add those up, we've only given away 98 of our 100 seats. So, Again, we choose a new modified quota different than, so we use a modified divisor different than that of our original divisor. In this case, they chose one that's actually bigger, 100.06 for each of these. Again, you will not have to decide on the modified divisor. Any problems that involve these methods, you will be given the modified divisor. So after we divide each of those by 100.06, we get these new modified quotas. The way the Hill-Huntington method is, you go, okay, what are the whole numbers that surround this decimal? For this one, it's 9 and 10. For this one, it's 7 and 8. For this one, it's 6 and 7. And for this one, it's 76 and 77. You find the arithmetic mean of those numbers, which means you multiply them and take the square root. Just like that. And that would be done in your calculator. After that, you use standard rounding rules. So 9.4 rounds down to 9. 7.4 should actually round down to 7. This might be a typo. 6.4. What are they doing here? All right, it looks like they must be rounding by the nearest 100, because if we use to the 8th, this rounds up to 8. This one becomes 6.5 and rounds up to 7, but they still kept that 76. So if I add those up, now I get a total of 100. Oh, no, I'm sorry. Let me re-explain that. I forgot this little note off to the side. So modified quotas are rounded down if they are less than the geometric mean and rounded up otherwise. All right, that's right. This one's really obnoxious. So we compare this number to the modified quota. If this number is less, if the modified quota is less than the geometric mean, it gets rounded down. If it's greater, it gets rounded up. 9.47 is less than 9.48. So I round down. 7.49 is greater than 7.48, so I round up. 6.49 is greater than 6.48, so I round up. And then 76.49 is less than 76.498, so I round down. So that one's complex. I'm not going to ask you to do too many of those, but you have the video for reference.